In this lesson, we study functions that are called monotonic, and we use something called the first derivative test to find when functions are increasing and when are they decreasing, the intervals over which they're increasing or decreasing. We'll also use the first derivative test to find the extrema for a function. The first thing we would like to discuss is what the sign of the derivative function in a particular interval tells us. So if, first of all, f is continuous, it's a continuous function on a closed interval, and it's differentiable at every point inside that interval. If the derivative function is positive at every single point in that interval a to b, then we say f is increasing. Okay, so if we can show the derivative is positive, it means function f is increasing on that interval, a to b. If the derivative is negative, then the function f is said to be decreasing. Okay, now remember that a slope being, or rather the derivative function being positive means that the slope of the line tangent to the curve is positive. The derivative function being negative means that the slope of the line tangent to the curve is negative. All right, let's see how this helps us. In this example, we are given a polynomial function of degree 3. It's x cubed minus 12x minus 5, and we're asked to find the critical points of this function. In order to do that, we need to find f prime, right? And identify the open intervals on which f is increasing and on which f is decreasing. All right, so in order to find the critical points, what I need to do is find the derivative function. Now, f prime of x is equal to 3x squared minus 12. Now, one thing that we want to remember is that they gave us a polynomial function, and a polynomial function is continuous on its entire domain, and it is differentiable as well. F prime will always exist. It'll never be undefined. All right, so with that being said, then the critical points will occur only when f prime of x is equal to 0. So the next thing I'm going to do is I'm going to set f prime equal to 0 and solve. So 3x squared minus 12 is equal to 0. If I find the solutions for this equation, then I have found the critical points. So when I add 12 and then divide by 3, I get x squared is equal to 4, which means x is equal to plus or minus 2. These are my two critical points. Now, what's really, really important is that these critical points divide or partition the domain of our function to create intervals. Now, these intervals, we're going to track the sign of f prime. We're going to track the sign of f prime in each of these intervals. So the first interval is from negative infinity to negative 2. There's another interval from negative 2 to positive 2, and then a third interval from 2 to positive infinity. So these two critical points created 3 intervals. Now, what's really important is we want to track the sign of f prime. So here we go. F prime, now let's not forget f prime is right, where is f prime? Maybe I scrolled up too far. Oh, there it is, perfect. F prime is right here. Now what we can do is, what might be easier is if you'll allow me really quickly, come back up here. Let me scroll just a little bit. There. If we come back up here and we factor, if you factor out of 3, then you'll have x squared minus 4, which is x plus 2 times x minus 2. So what I'm going to do is I'm going to choose a value from this interval. I'm going to plug it into f prime. I'm going to determine whether f prime is positive or negative, and I will be plugging the value from this interval into the factored form because it'll be easier to track the sign. So like f prime, for example, of, let's say, -3. So this first factor here is just +3, so I'll ignore that. When I plug -3 into this factor, it is negative. When I plug -3 into this factor, it is also negative. And so a negative times a negative is a positive. So what we just found out right now, or determined, is that on this interval here, f prime, the derivative function, is positive, meaning the slopes of the lines tangent to the curve in this interval are positive. All right, very good. Let's move on. Let's pick a value from between -2 and 2. Let's choose 0. Now, when I plug in 0 into f prime, this factor is positive, this factor is negative. We have a positive times a negative, and so this interval here, the derivative function is negative. Again, that means that the slopes of the lines tangent to the curve in this interval are negative. Finally, let's choose a value from this interval. Let's choose the number 3. When I choose the number 3, this factor is positive, this factor is positive, and so this interval is positive. All right, so I think we are ready to answer the question. And let's not forget the question. The question was for us to find the critical points, and we did that. The critical points are 2 and -2. And we want to find the open intervals over which the function is increasing and decreasing. So here's our final solution. The function is increasing on these two intervals, decreasing on this interval, and then plus and -2 are our critical points. Awesome. Just in case it's helpful to see a picture, this is the graph of our function, the cubic function, and -2 and +2 were our critical points. And notice that that from -infinity to -2, we are increasing, right? Just like we had said. So on this interval, the function is, we would say, monotonic. And then from -2 to 2, the function's decreasing. On this interval here, it's monotonic. And on this interval here, this third interval from 2 to infinity, it's increasing, it's monotonic. The function is monotonic on 3 separate intervals. So this is the graphical representation of what we found. Now, what's really interesting is this critical point here and this critical point there. The line tangent to the curve at those points is horizontal, right? So that's really interesting. So at these critical points, -2 and +2, the line tangent to the curve is horizontal. That is to say, the derivative is equal to 0 at those two critical points, which is exactly what we had found earlier. All right, now here is the first derivative test for local extrema. Suppose that C is a critical point of a continuous function f, and that f is differentiable at every point in some interval containing C, except possibly at C itself. Except for possibly at C itself. I need to change that. There. All right. Now watch this. Going from left to right, if f prime changes from negative to positive at C, then f has a local minimum. Let me just show you a quick little picture. If the derivative is negative, that means it's decreasing like this, and then it changes to f prime being positive. That means it starts to increase. So f prime being negative means it's decreasing. F prime being positive, that means it's increasing at some value C. Then this is a local minimum. All right. The next one says if f prime changes from positive to negative at C, then f has a local maximum at C. So listen, if you're going from positive to negative, f prime being positive means the function is increasing, and then f prime changing to negative means now it's starting to decrease, and that's happening at some value C. Then there's a local maximum at C. I hope the picture helps. Now, if f prime does not change sign at C, then there's no local extremum at C. But let's remember that C is a critical point. A critical point is where the derivative function is equal to 0 or the derivative function does not exist. So if I can just show you a quick picture really quickly, this would be a critical point, but there's no change in sign. So right here at C, right, this is a critical point because the line tangent to the curve at C is horizontal, meaning the derivative is equal to 0, right? So yes, C would be a critical point, but the function's increasing and it continues to increase, so there's no sign change. So this is an example of C being a critical point, but not a local extrema, not a local extreme value. It's neither a maximum nor a minimum, even though it's a critical point, even though the derivative is equal to 0 at this point. So what I would love for us to do now is I want to give us a function, and I'm going to ask us to find the critical points of a function and use the first derivative test to find the local and the absolute extreme values. All right, let's consider this example. All right, here we go. We have a function here, x to the power of 1/3 times x minus 4. We want to find the critical points of this function. Once we have the critical points, we can identify the open intervals on which this function is increasing and decreasing. And then finally, find the function's local and absolute extreme values. All right, let's start with the derivative of this function. So f prime of x is equal to, before I find f prime, I think it would be easier to find f prime if I rewrite my function by distributing x to the 1/3. So then this would be x to the power of 4/3 minus 4 times x to the power of 1/3. I think finding the derivative like that is easier. Remember that the power on x is 1, and so when you multiply x and x to the 1/3, you're adding the exponent. So it's 1/3 plus 1, or 1/3 plus 3/3, that's 4/3. All right, now f prime now is equal to 4/3 times x to the power of 4/3 minus 1, that is 4/3 minus 3/3, which is just 1/3, minus 4/3 when you bring down that power of 1/3, times x to the power of negative 2/3. I got negative 2/3 by subtracting 1 from 1/3. So it's 1/3 minus 3/3, which is negative 2/3. I can simplify this by writing it as 4x to the 1/3 over 3 minus 4 over 3x to the 2/3. Now, I can rewrite this now I would need common denominators. The LCD is 3 x to the 2/3, so I need to multiply this first here. I can show it, this first term by 1 in the form of x to the 2/3 over x to the 2/3. I'm doing this so I can actually perform this operation of subtraction. So this turns out to be 4x minus 4 over everything over 3x to the power of 2/3. All right, so there's f prime. I'm going to rewrite it. F prime of x is equal to this. Now, I can factor out the 4 from the numerator if I wanted to. So let me actually do that, actually. I think that's a good idea. 4 times x minus 1 all over 3 times x to the power of 2/3. All right, very good. There is the derivative of f. Now that we found f prime, what we want to do is find the critical points. Now, remember that the critical points of our function will occur when f prime is equal to 0 and where f prime is undefined. Notice that f prime will be undefined if x is equal to 0. Okay, so let me jot that down for us. So f prime of x is undefined. I'm just going to put UND, okay? Undefined for x equal to 0. If x is equal to 0, then that whole denominator is 0, and this function's undefined. F prime of x is equal to 0 when the numerator is equal to 0, and that's when x is equal to 1. So these are my critical numbers, all right? My critical numbers. All right. Now, these are the only places where our function might have an extreme value. How do I know if it's an extreme value? If f prime changes sign. All right. So this is what we're going to do. We're going to identify the intervals that we have. All right. So one interval is from negative infinity to 0. The other interval is from 0 to 1. And the third interval is from 1 to infinity. What we're going to do is track the sign of f prime. So f prime, let's say at negative 1. Now, I'm forgetting what f prime is. Where is it? There it is, right there. All right. So if I substitute in negative 1, the numerator is negative. Okay. The denominator, remember this 3 right here is the cube root. It means cube root of negative 1, which is negative 1, but you're squaring it, so it becomes positive. So the numerator is negative while the denominator is positive, so then this interval is negative. Let's track the sign, okay, everybody? Track the sign. Now, for this middle interval, I'll evaluate it at f prime at, I don't know, maybe 1/2, positive 1/2. The numerator would be negative, okay? And this denominator, remember, it's the cube root of 2, the cube root of 1/2, and then that squared. So this is positive. And so this is, again, a negative over a positive. Look at that. F prime did not change sign. Finally, f prime of, I don't know, maybe 2. So the numerator is positive, the denominator is positive, this interval is positive. Finally, we have a sign change. Okay, so first of all, notice that our function is decreasing on this interval and on this one, increasing on this interval. So it's increasing on the interval from 1 to infinity. It's decreasing on the intervals negative infinity to 0 and from 0 to 1. Now, because the sign does not change from this interval here to this interval here, that means we do not have an extreme value at 0, at x equal to 0. There is no extreme value because there's no sign change. However, there is a sign change from this interval to this one. So therefore, at this critical point, x equal to 1, we have an extreme value. Now, do we have a maximum or a minimum? Well, the derivative goes from negative to positive. That means it's decreasing and then it's increasing. So I hope that visual helps you. We have found a minimum. If f prime goes from negative to positive, that means we have found a minimum. The minimum is located at x equal to 1. And if you plug 1 into our original function, the function value is negative 3. So the minimum is located at 1, and the minimum value is negative 3. Now, one last thing before we move forward is this would be a local minimum and also an absolute minimum. And the reason we know that is because this function is decreasing from negative infinity to 1. I was going to say from negative infinity to 0, but really it continues to decrease all the way from negative infinity all the way to 1. The reason why there's two intervals here is because at 0, the function, the derivative function is undefined at that value. But anyway, it's decreasing from a negative infinity all the way to 1, and then it's increasing from 1 to infinity. So this is both a local and a absolute minimum. I'll show you the picture of the graph really quickly just to help us understand. So here is the minimum that we found. It's both a local and a absolute minimum. To the left of x equal to 1, to the left, the function is decreasing. To the right, it's always increasing. The reason why here, it's kind of hard to show with my, or kind of hard to see with my rough sketch here, but here, actually, this is a little more steep. If you were to zoom in here, there's actually a vertical tangent at the origin, and that's the reason why. So there's a vertical tangent right here at the origin. My graph, it's a little misleading. Vertical tangent here at the origin, which is the reason why the derivative function is undefined at x equal to 0. But in either case, this is both a local and an absolute minimum. All right, very good. Awesome. All right, check it out, folks. Within the interval from 0 to 2 pi, find the critical points of this trigonometric function, sine squared of x minus sine of x minus 1. Once we've found the critical points, we want to identify the open intervals on which this function is increasing and decreasing, and then finally, find the function's local and absolute extreme values. All right, first things first, folks, let's find the derivative function. So f prime of x, let's go. It is equal to, in order to find the derivative of sine squared of x, we're going to need the power rule. So we're going to say this is equal to 2 times sine of x, and then times the derivative of sine of x, which is cosine x, minus, and then the derivative of sine of x, again, is cosine x. And then the derivative of negative 1 is just 0. So this is the derivative function. What we want to do is find the critical points, and we can do that by finding when this derivative function is equal to 0. Before we do that, we should probably factor, don't you think? All right, let's factor out a cosine x. That would leave us with 2 times sine x minus 1. So this is the derivative function. I want to know when this is equal to 0. Remember that the sine function is continuous, and it's also differentiable over its entire domain. So the only critical points will occur when this function is equal to 0. So this derivative function is equal to 0 when cosine of x times 2 times sine of x minus 1 is equal to 0, which then implies that cosine of x is equal to 0, or when 2 times sine of x, oh, that's real sloppy, hold on, there, minus 1 is equal to 0. That is to say when sine of x is equal to positive 1/2. Now, we need to look at our unit circle between 0 and pi, and we need to know when is cosine of x equal to 0. We also need to figure out when is sine of x equal to positive 1/2. Okay, so let's see. Cosine of x equal to 0. Let's see. Let me see if I can change colors here. There we go. Cosine of x is equal to 0. That'll happen when x is equal to pi over 2 and 3 pi over 2. And you can look at your unit circle to confirm that. Sine of x is equal to positive 1/2. This will only be in quadrants 1 and 2. And this will happen when x is equal to pi over 6 and 5 pi over 6. So then these are our critical points. All right, very good. Now, these critical points partition our interval. And so we want to, remember our interval is from 0 to 2 pi. And so we want to track the sign of f prime. All right, so here we go. I'm going to do it like this. I need f prime. Oh, here's f prime right here, folks. This is f prime, okay, right there. So I'm going to go ahead and move this up like that. And these are our intervals, all right? The first interval here is from 0 to pi over 6, okay? The reason why it's 0, I'm just trying to write pi over 6 neatly, struggling. Okay, there we go. This 0 is from the original interval, right? The original interval they told us is from 0 to 2 pi. So 0 to pi over 6. The next interval will be from pi over 6 there. From pi over 6 to pi over 2. Okay. And then the next interval will be from pi over 2 to 5 pi over 6. And then from 5 pi over 6 to 3 pi over 2. And then finally one more interval, and that'll be from 3 pi over 2 to 2 pi. From 3 pi over 2 to 2 pi. All right, folks, these are all of our intervals, and what I'm going to do is I am going to track the sign of f prime over these intervals. All right, so here we go. So f prime, do you remember what f prime is? I'm asking because I don't. Let me see. Oh, there it is. F prime, I wonder if I can just write it right here. F prime of x is equal to cosine of x times 2 times sine of x minus 1. All right, here we go. Let's choose a value in here between 0 and pi over 6 and evaluate f prime, and we're only tracking the sign. All right, so why don't we do this, folks? Why don't we do f prime of something between 0 and pi over 6. How about pi over 8? Okay, now cosine of pi over 8 is in quadrant 1, and cosine is positive in quadrant 1, so I already know this first factor will be positive. Positive what? I don't really care. All I really care is to track the sign. So I know that first factor is positive. When I evaluate, and you can use your calculator to do this, but when you evaluate sine of pi over 8, you multiply that by 2 and then subtract 1, it's going to give you a negative value. Yes, in quadrant 1, sine is positive, but sine of pi over 8 is such a small value that when you subtract 1 from it, even after multiplying by 2, when you subtract 1, it becomes negative. So anyway, over this interval, we have a negative interval there. All right, cool. Let's keep going. F prime, we need something between pi over 6 and pi over 2. How about pi over, I don't know, pi over 3? Or maybe pi over 4 or whatever. Cosine of pi over 3 is 1/2, so this is positive. Again, I don't really care too much exactly what it is. I just really want to track the sign. Sine of pi over 3 is root 3 over 2, so then it'll be 2 times root 3 over 2, which is just root 3 minus 1, so that's going to be a positive value. So on this interval, we are positive. Notice the sign change. Okay, the sign change. All right, let's go for another value. A value between pi over 2 and 5 pi over 6. Something like, well, how about 2 pi over 3? That'll work. Now, 2 pi over 3, now we're talking quadrant 2, and cosine in quadrant 2 is negative, so I already know this will be negative. It's negative 1/2, right, everybody? But it's negative. And then sine of 2 pi over 3 is the same as sine of pi over 3. So root 3 over 2, root 3 minus 1. That's positive. So it's the same as before. But anyway, this interval is negative. Notice the sign change. Okay? And here, let's do f prime of... I don't know why my f looks so weird. Okay, there. F prime of pi, right? Let's do that. Now, cosine of pi is -1, but all I really care about is that it's negative. And then sine of pi is 0. 2 times 0 is 0. 0 minus 1 is -1, so it's negative. So then this interval is positive. Again, notice the sign change. Finally, f prime of something between 3 pi over 2 and 2 pi, maybe something that's convenient. How about something like, oh, I don't know, 5 pi over 3? I just chose that, okay? It's one of our special angles. 5 pi over 3, we're in quadrant 4, and cosine is positive there, so I know this will be a positive value. Positive 1/2, right? And then 5 pi over 3, in quadrant 4, you're negative. So this is going to be a negative value, 2 times a negative value, and then minus 1, so it'll remain negative. So this is a negative interval. All right, very good. Let me get rid of this here. Don't think we need it. All right, cool. So please notice the sign changes. All of these signs tell us about increasing and decreasing, and then whenever the sign changes, we have found an extreme point, extreme value. All right, so let's summarize our findings. All right, so here it is. We know we're decreasing on this interval from 0 to pi over 6, increasing from pi over 6 to pi over 2, decreasing from pi over 2 to 5 pi over 6, increasing from 5 pi over 6 to 3 pi over 2, decreasing from 3 pi over 2 to 2 pi. Now, I'm going to focus on the sign changes to tell me where my extreme values are. Okay, so let's do that now. All right, so we are going from decreasing to increasing. So then we just found that there is a minimum, and the minimum is located at pi over 6. We can actually find that ordered pair in just a minute. I know it's located at pi over 6. What is that minimum value? We can figure that out in just a minute. Next, though, we are going from, I'm looking here, from increasing to decreasing. So we're going from increasing to decreasing. So now we found a maximum. And the maximum is located, while we went from increasing to decreasing, between these two intervals. So it's located at pi over 2. Next, let's see, where are we at now? Now we're going from decreasing, this interval, to increasing, decreasing to increasing. So this again, right? Just sometimes we're better visual learners. So anyway, we found a minimum at 5 pi over 6. Cool. Now, from this interval to that one, we're going from increasing to decreasing. So we are increasing to decreasing. So then we have found another maximum, right? Right there. That's a funny point there. But anyway, a maximum at 3 pi over 2. All right, cool. Now, I would like to know the actual points, though. Like, what is the actual minimum value? What is that actual maximum value? So let's do that now. We have to evaluate our original function, the original function at each one of these inputs. Okay? Okay, just a reminder that this is our original function. So here we go. So we're going to evaluate our function at that first critical point, pi over 6. And at pi over 6, we found a little while ago that at pi over 6, we had a minimum. All right, so but what is that minimum value? So sine of pi over 6 squared minus sine of pi over 6 minus 1. Sine of pi over 6 is 1/2. So this is 1/2 squared minus 1/2 minus 1. So then this is 1/4 minus 2/4 minus 4/4. So then this is negative 5. Well, negative, negative 5/4. Sorry, negative 5/4. Okay, so what did we just find? That there is a minimum value of negative 5/4 at pi over 6. All right, I'll write that down in just a minute. Let us now evaluate our function at the next critical point, which was pi over 2. All right, at pi over 2. At pi over 2, we found earlier, because of that sign change, that we had a maximum. What's that maximum value? We're about to find out right now. All right, so here we go. So then this is sine of pi over 2, quantity squared, minus sine of pi over 2, and then minus 1. Sine of pi over 2 is 1, so it's 1 squared minus 1 minus 1. So then this is negative 1. So then the function f has a maximum value of negative 1 at pi over 2. All right, now let's evaluate our function at the next critical point, which was 5 pi over 6. You and I found earlier that at 5 pi over 6 there was a minimum. Let's find out what that minimum value is. All right, so then this is sine of 5 pi over 6, which happens to be the same thing as sine of pi over 6. And then sine of 5 pi over 6, and then minus 1. Sine of 5 pi over 6 is equivalent to sine of pi over 6, so this is 1/2 squared. So we did this already, minus 1/2 minus 1. We did this arithmetic already, and we found it to be negative 5/4. All right, so we just found that the function f has a minimum value of negative 5/4 at 5 pi over 6. The next critical point is 3 pi over 2. So this will be sine of 3 pi over 2, quantity squared, minus sine of 3 pi over 2, and then minus 1. Sine of 3 pi over 2 is negative 1, so it's negative 1 squared minus negative 1 minus 1. So it's positive 1 plus 1 minus 1, which is 1. So the function has a maximum value of 1 at 3 pi over 2. Now, at the endpoints, the function can achieve an extreme value at the endpoint. So let's check the endpoints as well. Now, the endpoints are 0 and 2 pi. So f of 0, which is sine of, 0 and 2 pi are the endpoints. 0 and 2 pi are coterminal angles. So these function values are going to be the same. So actually, let's do this. Let's save ourselves a little time and say f of 0 is going to be equal to f of 2 pi. So then this is sine of, so I don't have to do it twice, right? So sine of 0 squared minus sine of 0 and then minus 1. Or I could have used 2 pi. But anyway, sine of 0 pi is 0. So this is 0 squared minus 0 minus 1. So this is equal to negative 1. So let us conclude now. What I want to do is I want us to look over all of our minimums and maximums, and I want us to identify, so we found all the local mins and local maxes. I want us to identify the absolute maximum and the absolute minimum on this closed interval. So this is a summary of our findings. We found a local maximum at pi over 2 and at 3 pi over 2. The local maximum at pi over 2 is negative 1. So that means nearby pi over 2, like in the neighborhood of pi over 2, negative 1 is the largest function value near pi over 2. 3 pi over 2, around 3 pi over 2, or in the neighborhood of 3 pi over 2, 1 is the largest function value. It also happens to be the absolute maximum on the entire interval from 0 to 2 pi. There are local minimum values of negative 5/4. It happens at pi over 6 and again at 5 pi over 6. Between 0 and 2 pi over the entire interval given, there is no other function value that is less than negative 5/4. So negative 5/4 is a local minimum. It's also an absolute minimum.